Okay, my name is Todd, and today we're going to talk about sensitivity, specificity, and other things related to the quality of a test, such as positive and negative predictive values and negative and positive likelihood ratios. First up is sensitivity and specificity. Sensitivity is assuming that you actually have the disease, that's this truly positive column. What are the odds that the test will say you have the disease? And in this case, 99 out of a total of 100 patients is 99% sensitivity. Specificity is similar, but if you don't have the disease. So if you really do not have the disease, what are the chances that the test will also say you don't have the disease? In this case, still 99 out of 100 people that truly do not have the disease, it's going to say negative. We have a 99% specificity. Now, something that is in some way similar but not the same thing is positive and negative predictive values. Whereas sensitivity and specificity say you have the disease, what might you get from your test? The predictive values say you have this test result, what are the chances that you actually have the disease? And so in this case, out of the 100 people going this way who had a positive test, 99% of the people actually had the disease, and so we also have a 99% positive predictive value. Same thing here, I chose these numbers because they're symmetric. Out of the 100 negative test results that we got, 99% of those people actually don't have the disease, and so we have a 99% predictive value. Now, in a way, these are more useful because we often don't know if you truly have the disease. We're using the test to try and figure that out. So if you walk in and go to the doctor and they give you some test and it comes back positive, this is more often than not the number you want to know, because you're trying to go from I have a test result, do I have the disease, instead of sensitivity and specificity, which is I have the disease, what was my test results? Now, another thing that we can calculate is the positive and negative likelihood ratios. Now, these are, for the positive, if you get a positive test, how much greater odds do you have of actually having the disease? It's another way of trying to get from you had a positive test, do you actually have the disease? Or you got a negative test, do you actually not have the disease? Now, I was very specific to say that, like in this case, we have 99 times the odds. I said odds very specifically because you can see we don't have 99 times the chance. If half the population has the disease and you multiply that by 99 times, you don't have a 4,000 some odd % chance of having the disease, because logically that doesn't make sense. You have 99 times the odds, and I'll show you that in a second. But first, what it actually is what is the chances that if you really have the disease, you got a positive test. So in this case, 99 out of 100, that's basically just our sensitivity, divided by what are the chances that if you really do not have the disease, you got a positive test. And so that's kind of the opposite of specificity. If specificity is if you truly don't have the disease, what are the chances it'll say negative? And what we need for the denominator in our likelihood ratio is if you truly don't have the disease, what are the odds it says positive? And so it's your sensitivity divided by either 1 or 100% minus your specificity. And so in that case, that's going to be 1 over 100, so 1%. And that's why 99% divided by 1% is going to give you a 99 times. So you have 99 times better odds of having this disease if you get a positive test. The negative is very similar. It's what are the odds that if you truly have the disease, it'll say negative, and so that's kind of the opposite of the sensitivity, 1 or 100% minus your sensitivity, divided by if you truly do not have the disease, what are the chances that your test came back negative? And so that really is just your specificity. So in either way, if people truly having the disease go in the numerator, and people that truly have truly do not have the disease go in the denominator. But you have to use all 4 of these numbers to get either one of these. You can't just take the 99 divided by the 1. It only works like that because everything is so symmetrical. In later examples, you'll see that doesn't make sense. Now, I'd like to explain what I meant about increasing the odds and not the direct chances. So this is the way that runs the math, and so 50% of the population has the disease in this case, and by the time we run our test, we'll be able to increase that knowledge up to 99% sure they have it or 99% sure they don't. And these likelihood ratios are a way of reconciling and increasing our knowledge and our confidence, right? But it truly is the odds. And so if you think 50% is a 1-to-1 odds, right? One chance you'll go one way, one chance you go the other way. Now to get to the positive predictive value, you actually take the odds and multiply them by your positive likelihood ratio. So now we have 99-to-1 odds, but then you have to turn that back into a percent. And that's why you don't just take 50% and multiply it by 99. You take 1-to-1 odds, multiply that by 99. Now you have 99-to-1 odds, and when you turn that back into a percentage, you have 99%. Similarly, with the negative likelihood ratio, you can take it from 50% multiplied out, and now you have this right here is the equivalent to our 99-to-1 odds that you have the disease. And so it's a little goofy because if you just turn this into a percent, now you only have a 1% chance of having the disease if you got a negative on this test. But we want to know what are the odds you don't have it, or the percent chance you don't have it, which is your predictive value, and so you just do 100% minus it. And so you can see that we went from sensitivity, specificity, we got likelihood ratios, and all we need is this other information, and we can calculate our positive and negative predictive values. And the two ways to get to this information will give you the same number. So now what I'm going to do is change our starting conditions so everything's not so nice and symmetric and see what actually happens. So in this first case, our sensitivity and specificity are 99%. I went out of my way to make sure that would still happen. But now if you look at the general total, we have a lot more people that don't have the disease than do. This is a rarer disease. Now when we were talking about calculating likelihood ratio, we actually found that all you need to know is sensitivity and specificity to calculate those. And we find that our positive and negative likelihood ratios are still 99. And if you invert this out, you could say this is 99 times less odds of making that work, right? But what's weird is that if you go and just kind of mentally get a gauge of what that positive predictive value is going to be like, it's kind of fishy that if you have a positive test, it looks like slightly less than half the time you're actually going to have the disease. And if we calculate our positive and negative predictive values, we find that is exactly what we find. It's slightly less than 50%. And remember, this is kind of what we need to know as a patient, right? I just got a positive test. But because it's a rare disease, now there's only a 50% chance I even have it. It's kind of weird to think about. And the reason why that makes a difference is because now not even 1% of the population has the disease. And so increasing this, we have a 99 times likelihood ratio. We're increasing the odds of us having the disease by 99 times. But that's only really going to take us up to here. And we could look at those calculations. When you run the math on this, we have 0.1-to-1 odds. And so even though we're increasing our odds by 99 times, which is a super significant number, especially when you think of like lecture said, greater than 10 is very significant. We increased 99 times odds, but because it was so rare to begin with, we were still slightly under a 50% chance. Now the opposite happened for the negative odds ratio. Because it's a rare disease and we have a pretty good test, it makes us 99 times less likely. We reduced the odds by 99 times, and now we are ridiculously confident that if you get a negative test, you don't actually have the disease. Because look at that, out of 9,901 tests, only one person is going to actually have it. So it's kind of great for our negative predictive value and slightly harmful for our positive predictive value. If we take an even more extreme example, you can see the kind of things that make diagnosing rare diseases very tricky. Now we have even an even greater chance of just people in general not having disease. 0.1-ish% of the people have the disease. And so even though we still increase the odds by 99 times, 99 times of really crappy odds can still potentially be a really crappy chance of actually having the disease. And so in this scenario, if you have a positive test, it's still really likely you don't have the disease, which is really weird to think about. And of course, our negative predictive value got even better because we're taking even smaller odds. I guess this is the odds and this is percent, but we took a really small percent chance and reduced it by an even greater amount of an odds reduction. And so it just, if this was a real test and it came back negative, you can walk home pretty confident that you don't have that disease. So this is back to our original numbers. I want to reset your head because now I want to change the numbers in a different way. And it's going to do something a little different for you. So this time, instead of increasing just the number of people that have it, I increased the number of negative tests. And what's weird about that is this time our sensitivity got really messed up and our specificity got great. Because if you really have the test, there's actually a greater chance that, or if you really have the disease, there's actually a greater chance that you got a negative test than a positive test. Super weird to think about. However, when you look at the predictive values, if you got a positive test, there's a 99% chance you have the disease. And if you got a negative test, you still have a 99% chance that you don't have the disease. And it's really to think about, it's tricky to think about reconciling this less than 50% sensitivity with the fact that if you get a negative test, it's still really likely that you don't have the disease. And the reason why is because it's rare. And it makes sense. Most people just aren't going to have the disease regardless. And so it all works out. Now, where you start to see something more interesting is looking at the likelihood ratios. In the likelihood ratio, now that everything's not symmetrical left to right, we don't have the same positive and negative likelihood ratios. When you invert this to make it a positive number, the positive, you're basically 5,000 times as likely if you get a positive, but if you get a negative, you're only like half as likely. And when we look at the odds, we can start to see why this makes sense. If you're starting out with a 2% chance, right? And your odds go up by 5,000. 5,000-ish is what it takes to get you from having a really low percentage of the population having it up to now we're 99% confident. So to take this, the odds version of our population percent, and turn it to 99 to 1 odds, you would need a test that has a likelihood ratio of 5,000. But now if you look at it, we're really going from, with the negative test, we're going from roughly 2% of the population having the disease to now there's only a 1% chance that you having disease. It's still cool because if you get a negative test, it's still really likely that you don't have the disease. But then this makes you question the quality of the test. If you're only halving the chances of having it, you're going from a 2% chance to a 1% chance. And that's nice, and I would certainly feel good about having a negative test, but then it's like, how much did that really do? And that's one of the reasons why having a likelihood ratio of less than 10 is not as significant. It's like, what did this test really tell me? But in this case, what this test really told me is that it's still really, really rare that I have the disease. There's still a 99% chance I don't have the disease. All right, so I am a fan of extreme examples, and so I took the negative test and multiplied it by 10 again, just to show you what kind of stuff this is doing. So now we only have a 9% sensitivity. The vast majority of the people that actually have the disease, the test is going to show up negative. However, we still have a 99% negative predictive value because the population got even rarer. And then now you can look and see what's happening with our positive and negative likelihood ratios. This about doubled because it went from roughly 2% to just a little over 1%, all the way up to 99%, that requires a 9,000 times greater odds of making that happen. And then our negative likelihood ratio, the test became even more worthless because all this test, going for a 99% predictive value means going from a 1.09% chance of you having the disease down to a 1% chance of having the disease. And so, like, you have 10% better odds of having the disease, of not having the disease if you get a negative test. So this is an instance where, like, the negative test is completely worthless, almost. But you still have to reconcile with that most people don't have the disease. It's still, even if you get a negative test, it's just weird to think that there's still just a really small chance you have the disease just because most people don't have the disease. However, in the case of this test, if you get a positive test, you better go straight to the doctor and figure out what you're going to do for your treatment, because you brought, out of a rare disease, you brought it up to a 99% chance that you actually have it. Your likelihood ratio is 9,000, and yeah, the positive test is significantly meaningful. So the ultimate takeaway from this is that just looking at just sensitivity, specificity, or just positive negative predictive values, or just positive negative likelihood ratios, if you look at any one on its own, they all have their issues. We saw a case where the positive likelihood ratio was 99, which is amazing, and yet there was still only a 9% chance. We see examples like this where the sensitivity and specificity are super weird, and yet it still brings it up to those 99% chances. And we saw examples where those were both good, but that was really bad. Like, because any statistic that you run, the number of people that have disease is important to take into consideration. And that's where looking at all of these in conjunction is very useful. It's a good thing to do. And the nice thing that we know is that if you have the sensitivity specificity and you can figure out the percentage of people, the population, it's a little tricky, but you can run the math on these to get this, and then you can run the math to get these. And so you really need 3 numbers, and you can calculate the rest. And then you still have to make a judgment call on when someone gets a positive or negative test back, what does that mean? What does that inform you as a clinician of, well, does this person have the disease? That's ultimately what we're trying to go for, is a positive or negative test back to people that really have it and people that don't. And all of these are limited in their own right. And together they're more useful, but it's ultimately still chances and odds. And so you have to use your best judgment and pick treatments according to what you think is most likely going to be happening. And calculating these is going to potentially help you out. If you guys have any questions, come track me down. This is my best effort to make this all make sense and see the relationship between all of the numbers, but of course, there's a good chance with the number of people watching that somebody is still confused and that I could have explained something better or differently. So I am all for feedback. Let me know what worked, what didn't work, and then ideally the next time I make a video like this, it will be better for all of you. Thank you and have a good day.